An examination of the origins and viability of both relativity and quantum mechanics begins with the description of radiation and light. This diagram of variable electric and magnetic fields is a typical representation of a traveling wave. We can break down the traveling waveform. Accelerated movement of a charged particle produces radiation. Joseph Larmor, a Scottish physicist, did this work over a century ago. His starting point was Maxwell's equations. For electrons with velocities well below the speed of light, instantaneous radiation is calculated by the Larmor formula. Electrons only radiate when accelerating. They do not radiate when at constant velocity or during deceleration. A single radiation is not light. It takes another radiation with a reversely polarized electric field separated by time to produce light. For our purposes, the minimum configuration of light consists of two alternating polarization radiations. A single electron undergoing back and forth oscillation produces light. To be visible to the naked eye, many electrons must contribute. The same dynamic is true for a positively charged nucleus. The human eye contains movable electrons that respond to the alternating polarizations. The human vision system measures the time between radiation fronts, and the brain interprets those times as different colors of light. The stylized academic waveform is deficient because it does not account for particle accelerations and decelerations. The Larmor formula for charged particle radiation varies by the square of linear acceleration. This formula only works for particles at low velocity relative to the speed of light. For faster particles, we use the Lennart-Weichert formula, which adds a velocity factor. In a radio antenna, the greatest acceleration occurs at the ends, where the velocity is 0. At the feed point, the acceleration is reduced, but the velocity is high. In between, there's a trade-off between acceleration and velocity factors. The waveform is not a smooth, sinusoidal curve as the academic representation suggests. The exact transmitted waveform would be difficult to calculate because many separate electrons add to the total effect. The waveform is also affected by the contribution of the antenna and the transmitter with feed lines, etc. Nevertheless, half the waveform is zeroed out due to particle deceleration. For subsequent analysis, useful in atomic spectral interpretation and relativity scrutiny, the waveform can be simplified. This is a digital representation of the up and down electric field polarizations. A single up-down pair is the smallest segment of what is considered a waveform. A single light waveform is represented as a dual radiation front. The up-down pair is in a circle. Alterations of the distance between fronts produces frequency modulation. Alterations of the amplitude of the fronts produces amplitude modulation. A continuous collection of equally spaced radiation fronts represents a power delivery capability. It is proportional to the frequency. While an electron undergoing acceleration produces radiation, the reverse is also true. A radiation front accelerates a charged particle via the Lorentz force. In this way, a wave delivers power to a charged particle. This is how a radio antenna picks up a signal from the air. Light generation, both natural and man-made, has time-separated radiation fronts. This is the alternating polarization, or AP format. This is represented by the blue circle transmitter, with one side of the antenna active, followed by the other side. For relativity analysis, another method of light generation must be employed. The red circle transmitter uses simultaneous generation. It is called a relativity superbulb to distinguish it from a typical AP transmitter. It produces a single wavelength of light at a time. For the analysis of fast-moving light generators, it is important to have this methodology available. With light described, an examination of relativity can be undertaken. This understanding is also crucial for accurately interpreting the light generated in a gas discharge tube. The hydrogen gas discharge tube launched atomic analysis in the early 20th century.